Good day, good afternoon, everyone. My name is Alberto Montilla, and with me is Veronica Acosta. She's Business Development Manager at Spatium and UTEP alumni. Today, I'm going to be talking about space communications and the interplanetary internet, and I hope this subject is as exciting to you as it is for us. Just a quick intro. I am the CEO at the Spatium Corporation. We are a company aiming to creating the interplanetary internet. I'm also board member at the Interplanetary Networking Special Interest Group. This is a chapter of the Internet Society. And my background is in communications and networking. Have been doing communications and networking in different fashion for more than 25 years now. And also early in my career, worked as assistant professor in primarily radio subjects like radiation and propagation. So with that being said, let me start, and I'll talk about the agenda a little bit. It's basically the session or the lecture is organized around three main topics. First one is the foundations of space communications. We call it Space Comms 101. Then we're gonna double click on the topic of the interplanetary internet and how we're moving towards enabling data communications in the solar system. And then we're gonna talk a little bit about the why are we doing this, and basically is the fact that humanity is moving from a space exploration where we have been doing that for the last would say 60, 70, 80 years to the space economy. So let's go to the first topic, basics of space communications, and I'm going to start with an extreme example of space communications. This is the Voyager 1 spacecraft. This is the first human-made object that reached interstellar space around 2012. Think of it that it was launched in 1977. Internet didn't exist by then, and I think the first paper about TCP/IP came out around 1978. So that gives you an idea of the type of technology that is on board the spacecraft. What it has achieved is amazing. Not only is the first spacecraft that reached interstellar space, but also think of some of the features. The spacecraft, it's around 15.1 billion miles. That means 162 times the distance from Earth to the Sun, so basically astronomical units. It is moving pretty fast, 37,000 or close to 38,000 miles per hour. And the one-way light time, basically that means the time it takes for light to go from where we are to where the spacecraft is 23 hours and a half. And why is that important? It's extremely important because radio waves, optical waves, basically communications move at the speed of light. So what that means is that when we send a message to the Voyager 1, we have to wait pretty much 2 days for it to come back. Now, when we double click on that in terms of communications, the first thing that is very interesting to me is the amount of information that we're getting back. This is so far that we receive approximately 160 bits per second every time we connect to the Voyager 1. And for those who have been following its evolution, Voyager 1 had a major troubleshooting in the past weeks because the communications were basically lost. The data that was coming a little bit kind of garbled, and the deep space network complex in Madrid, one of the three complexes, we're going to talk about that in a second, had to align all 6 antennas in array to be able to get enough signal to understand what is going on. And that the reason is that the signal level that is received is extremely low. It's one at minus at the power of minus 16 watts. So very, very faint signal level or power level. And the communications between the Voyager and Earth is done via the X-band 8 gigahertz. If you want to know more details about the Voyager, it's our favorite spacecraft. You can go to the NASA JPL website, and there is a specific page dedicated to the Voyager and the data being received. So I'm highlighting this example because communicating in space is complex, and we're going to go through some of the details of why it is difficult to do. Let's analyze the effect of distance in space communications, which is one of the big topics here. You know, we said, hey, Voyager, it's in interstellar space. What happens in between? So let's try to get some sense of, through numbers of what is going on. First, let's look at the distance. You know, when we think about distances in space, we typically divide the distance or the volume in three main areas. The first one is what is around Earth, the Earth orbit, and there are multiple orbits within Earth. As an example, the ISS, the International Space Station, it's moving around Earth at an altitude of 250 miles. So that's the distance. It's relatively short distance. However, when we think about the last orbit, the geostationary orbit, where the geostationary satellites are hosted, we're talking about 22,236 miles. So it's a very large distance. What this causes is the following. What this causes is the farther the distance or the longer the distance, the communication delay becomes larger. Why? Because the wave that is traveling at speed of light will take X amount of time, and this time will increase with the distance. So in the Earth orbit, we're talking about delays that goes from mere milliseconds to hundreds of milliseconds. And many of you might not remember because this is some technology has evolved so much, but beforehand the only way to communicate across continents was through satellites, and those satellites were in geostationary orbit, and the delay you would experience was between half a second to a second. And you start noticing that if you're on a telephone call, you start noticing that, hey, you are talking and the other person is not responding immediately. The other effect of distance is signal loss. The longer the distance, the more power, radio power, optical power is lost, and the end receiver receives less amount of energy. The reason is that the loss of the signal is, proportional to the frequency and to the square of the distance. So the longer the distance, the signal energy or power is going to be lost at the power of 2 to that. And what happened is the following. Then if you think about what happens in scenarios with longer distances, like what happens within the solar system. Well, the solar system is the distance between the moon and Earth is 230,000 miles, almost 240,000 miles. And now you start experiencing delays that are not in milliseconds, but are in seconds. If you think about Mars is between 35, depending on the 2-year cycle between Mars and Earth. Mars is between 35 to 215 million miles. So we're talking about delays that are in minutes, even to hours, if you think about round trip delay. And in interstellar space, and the closest system is Proxima Centauri, we're talking about close to 25 trillion miles. And now we start talking about light years, which is basically takes 4.3 years for light to get there. The conclusions you get of the effect of distance in space communication is basically two. The first one is, believe it or not, real-time communications. There is a point in which real-time communications is simply not possible, because you have to wait. If you have to wait for a response, you know that this response will come from hundreds of milliseconds to days to years later. So you cannot have a real-time conversation anymore. The second part of it has to do with signal loss. which is the longer the distance, the longer the losses. And the way we have overcome or partially overcome this is by having bigger antennas. And when we say bigger antenna, we're talking about bigger parabolic antennas because these communications happen the bands. So you see, like, the biggest antenna probably right now in the deep space network is around 70 meters of diameter. And then better electronics. For those who know about electronics, you know that every electronic component contains noise, and there is a relationship because of thermodynamics between noise and between temperature and noise. So we're talking about electronics that are, for example, in cryogenic temperatures, so that the noise gets to the lowest possible levels. And what all this means is that it becomes more and more expensive as the farther you want to travel. So think of it: distance in space communications causes delays and major signal loss. We're going to talk about that later today. Now, the second big topic, if as distance have a strong effect in space communications, the second one is disruptions. There are a lot of disruptions happening in space communications, and the reason is the following. On one hand, you have celestial mechanics happening. Planets rotate, they translate, they move relative to each other. There are things like conjunctions. As an example, we have the dark side of the moon, where there is never line of sight with that moving area. Then the relationship between the movement of Earth and Mars, it is a 2-year cycle. For example, there is a moment of time in which Earth and Mars are in conjunction with the sun. What that means is that Earth and Mars cannot see each other because they see each other through the sun. And imagine the effect that has in communications. So in general, disruption causes, one, that there is no line of sight, and that's required for point-to-point communications, like a radio link or optical link requires line of sight. And the effect of not having line of sight is the loss of signal, loss of communications. So how do we solve for that? Think of it: big effects, distance, and disruption. So how do we solve for that? Well, there are multiple techniques that are commonly applied in space communications. The first one is the use of a relay satellite. That's pretty common on Earth and also in other planets like Mars, for example. The relay satellite, as the name indicates, is a satellite a communication satellite that connects two moving elements. So, for example, it could be an Earth ground station with a spacecraft that is in space. One example is the Hubble telescope or the International Space Station. They do use the tracking and data relay satellite system, TDRES, that is maintained by NASA. They at moments where the ISS or Hubble telescope don't have line of sight with the ground stations, they use TDRES as the TDRES system as a relay satellite. And you see on the screen, some of the satellites that makes the TDRES constellation. And TDRES is in the geostationary, operates in the geostationary orbit. Another way to minimize disruption is looking at it from the planet, in this case from Earth perspective, which is how do you achieve 360-degree coverage so that you can cover every area of the space volume. On Earth, it is done by placing ground station antennas with a minimum of 3 around the world. And they basically requires 120 degrees of separation to achieve the 360 degrees, the whole circumference. In the planet vicinity, and this is on the Earth vicinity, is basically having satellite networks. And we all know about Starlink. I mentioned TDRES. These are just two examples of constellations, Inmarsat in Geo, Global Star in Leo, that are placed to perform basically relay functions. This has been going for many decades. Started with telephone and television satellite relays, and now they are being used for any sort of data relays. And basically what happened is that depending on the movement of the planet, there are different type of orbits. So for example, for Earth, the Earth vicinity is divided in three main type of orbits. The first one is the low Earth orbit, LEO, which is very close to Earth. This orbit is not geostationary. What that means is that the relative satellite of the movement of the satellite is different than the movement of Earth. So the satellite is never in the same place. That's why you require huge constellations to be able to cover the whole thing. Then you have the mid-Earth orbit, MEO, and that one also, it's not a geostationary orbit, and therefore you also require a constellation of satellites, but a lower number of satellites. And then you have the geostationary orbit, GEO, and this is where all started. These satellites are at geostationary orbit. What that means is that the satellites are always seen in the same place from any Earth location, which is fantastic idea for relay satellites. The drawback is that those are, as I said before, the geostationary orbit is at 22,000 miles, like 35,000 kilometers, and you have longer delays and you need more expensive electronics and antennas to be able to communicate with them. So let's look at another example. We talk about a Voyager as an example of a spacecraft. Now I'm going to give you the example of the extreme ground system. That's the best ground communication systems for space that humanity has, and this is the NASA Deep Space Network. It's a collection of antennas of different sizes that are located in three main locations, 120 degrees, give or take, separated. Goldstone, Madrid, and Canberra in Australia. And they basically connect to all our systems that are in spacecrafts that are in deep space, whether it is Mars, Moon, and beyond, like Voyager. You can go to the ice.nasa.gov to basically see real time which antenna, which system is connecting to what spacecraft, and it's amazing. The example here is the Mars Odyssey being connected to the Goldstone 26 antenna. Now, because we have many engineers and students in the audience, just wanted to give you a hint about how you design these networks. And you start with the physical link, the space link. And the space link, the design of the space link is not very different from the design of any communications link, for that matter, in this case, radio link, where you calculate the power budget. It's also called the link budget, which is the how many power needs to be transmitted in order for the receiver to properly decode the signal. So basically, the starting point is that there is a minimum signal level, minimum level of energy or power that has to be received for the system to be able to demodulate the signal. These signals are modulated. That's the way signal contains information. And the amount of signal level depends heavily on the specific modulation and the specific encoding used. So there is a dependency of the type of electronics that you have. So the main formula, and I'm putting it here using the straight values. It's basically the power received is equal to the power transmitted multiplied by the antenna transmitting antenna gain multiplied by the receiving antenna gain. And then all of that is divided by the free space loss that has dependency on the frequency and the distance, multiplied by the losses in the transmitter, and multiplied by other transmission miscellaneous loss. So transmitter losses include things like the loss of signal of doing as they go through the cables, through connectors, through splitters, etc. And miscellaneous losses include loss of polarization, fading, and some, as for example, atmospheric events if that link crosses the Earth atmosphere. And this is an example. Going to an example, this is the Mars Odyssey orbiter link budget for the forward link. That's basically forward link is Odyssey transmitting to Earth. And I won't go into any details, but you have the details here of the expected receive levels, and as you go through, analyze the frequency, analyze the type of modulation, transmit power, circuit losses, etc, etc. So for every spacecraft out there, one of the calculations you do very early on is the link budget to ensure that the design holds. There is in the scanso.jpl.nasa.gov, there is a whole set of documentations about how you create, or not how you create, space links, link budgets for the different missions and different spacecrafts out there. So it's very interesting if you are, if you have some interest on that. Now we have seen the Space 101 effect of distance disruptions in space communications, how you overcome that by placing antennas around, by having the right amount of energy, the right type of antennas, using relays, for example. So that allows you to build a network that basically is able to send information from one point to another point. So now let's see, and let me go back for a second. Now let's talk about how we move from that to a true data network. And think of the following. When we talk about the interplanetary internet, there are two main components. The first is internet. In internet, you can send data openly between any two endpoints without much knowledge of the underlying links that are happening. All you need to know is the IP address of the other end, and magically they are connected, right? So the whole idea is that we extend the same level of concept to a space in which you can, from Earth or from any planet, any spacecraft, you can address any other point without necessarily knowing what is the underlying network that this is going through. The challenge, and that's why we call it interplanetary internet, is that, as you will see, we're doing this in an environment where distances are very, very high, big, and disruptions are very, very frequent. So we're going to talk about those two. So think about how we build a space network, and now we're talking about data transfer in space. This is, just something to highlight, because you always are going to hear about telemetry, command, tracking, navigation, communications, and what these terms means. The first is telemetry. Is typically, as the name indicates, is science, engineering, imaging information that you get back from space. You are basically getting the results of the, whatever is measured. Then from Earth, another typical type of information that is sent to the spacecraft is commanding, which is basically control functions on the spacecraft. And these control functions may be to control the spacecraft itself, or some of the payloads, like there is a camera, well, you want to take a picture, or there is a video camera, you want to get that feed. So these are commands, payload commands versus spacecraft commands. Then tracking and navigation. One underlying things where communication is very useful is to let each component understand direction, speed, location. So helping the spacecraft to navigate, and helping mission control, or spacecraft control in this case, to understand where the spacecraft is as well. So this makes good uses of some of the features of the electromagnetic theory, things like a Doppler effect that allow us to know exactly how a spacecraft is moving, in which direction, whether it is coming or going, etc., etc. And last but not least, communications, which is the act of using the spacecraft. Think of a relay, for example, to send data that has destination of another spacecraft or another user. Typical example is the relay satellite. So these are typical terms that we talk about in space communications and space networking. So the way data communications is established is using the a data protocol stack. Each protocol has a role in the OSI model, starting with establishing the data link to allowing the network layer. So data link is between two endpoints, A to B. Then the data layer allows, these are protocols that allow to move from multiple elements to go from an origin to a destination. And then you have the transport layers that basically adapts the network or between the application and the underlying network elements, like establishing sessions, for example, and delivering, information in a very specific format. And then you have the applications that, applications could be of many types. So in space, the CCSDS, which is the Consultative Committee of a Space Data System, is the standardization body for protocols. Basically, CCSDS is formed by space agencies and also by some observers, companies observing and helping space agencies moving this along. And there are many protocols that have been established over the years, like CFDP, which is the File Delivery Protocol, SPP, the Space Packet Protocol, and then some Space Link protocols. There is a myriad of standards for space data communications. But one of the things that has been missing, it's basically how to perform networking at interplanetary distances. And this started back in around 1998, where the first concept of the interplanetary internet or the solar system internet was established. And these discussions emerged as the first missions to Mars starting to be planned and engineered, where there was a need for performing relay functions. That's still working till date. But these relay functions, one of the key discussions was, hey, how do we bring data communications? How do we bring TCP/IP to Mars? And after initial analysis, it came clear that the current protocols that we use here on Earth, TCP/IP, that enables the entire internet, had major architecture and performance issues when applied at interplanetary distances. And let me give you two examples. First example is centralized infrastructure. We use something called DNS, the domain name system in the internet. That's basically what translates google.com to a specific IP address, which is the address of the node. And this system is fully centralized. So what that means is, for example, if I am in Mars and I type google.com, first I need to resolve that through DNS. So I have to send a message to Earth. In best case, that would take 7 minutes. I'm going to get the response back. And then with the IP address to basically send the message I want to send. By the time this happens, the communication opportunity, because everything is moving, the communication opportunity or the contact may already be off. So there are many situations in which the protocols cannot even converge because the time it takes to establish the protocol is longer than the typical communication opportunity. That has to do, for example, with certain security protocols on the internet that takes around the exchange of 7 messages. So imagine exchanging 7 messages between Earth and Mars. Multiply 40 minutes delay by 7. At the end of the day, it was declared, it was well understood that TCP/IP didn't work at interplanetary distances. And at the time, being served and people from the Jet Propulsion Laboratory worked hard to come up with a new solution, a new architecture. And this architecture became the delay and disruption tolerant networking architecture. And I'm going to double click on that in the next few minutes. So think of it that the whole title said all. It is networking that is tolerant to delays and disruptions, which, as we said before, are the two key things that happens, when you are in deep space, when you are at interplanetary distances. So DTN is a networking technology that enables the reliable transfer of data across the network elements when the propagation delay is high, highly variable, and or just very high. The data transmission is performed automatically, so basically pretty much like the internet. But even when one or more network links are not available during long intervals. And the main internet working protocol in the DTN protocol stack is the bundle protocol. So those who work on the delay and disruption tolerant networks, we typically interchange frequently DTN with bundle protocol. Bundle protocol is the main protocol for DTN in space. So let's look a little bit more on this and some key attributes. I won't get into a lot of detail, but want you to get an idea of how different this is. So first is the bundle protocol runs as an overlay protocol over multiple network and link technologies. So if you see in the screen below the text, you, for example, see that on mission control, the bundle protocol runs over TCP/IP. On the other hand, on the Mars rover, the bundle protocol runs over LTP. LTP is the Lead Ladder Transmission Protocol. It's a protocol that is purposefully built for space links. Space links. And the reason the bundle protocol has this flexibility is to be able to adapt to the different environments. Earth, where you have mission control, you have the ground stations, and space, where you have these long space links. The second attribute is that networking can occur both scheduled, that's basically planned, or via opportunistic contacts. And let me elaborate on that. Think of the following: the way planets move around relative to each other, it's 100% predictable. We know, we have the ephemeris to Mars. We know it is a 2-year cycle. We know where Mars is going to be at every point of time. So we can schedule the times that, for example, we can have a specific antenna pointing to the relay in Mars. So those are contacts that are scheduled. In addition to that, we have opportunistic contacts, which are contacts, for example, if you are in the ground surface, for example, lunar surface, you just may want to send a message at any point of time, and it would be opportunistic because the satellite, the specific relay satellite, is just having a pass over, that device. And last but not least, that's one of the most important attributes, because it's very different from the traditional terrestrial internet, is that the network itself performs store and forward. That is, every node have basically an ability to store the bundles, which is the unit of data traffic. And why? Well, it's very simple. You are receiving data from, let's say, ground. You are the ground station. You are receiving data from mission control. But the Mars relay satellite is not in line of sight. So you have to hold that data until you can establish a contact with the relay satellite. The same way the relay satellite, once it communicates with the ground station and receive those bundles, then it has to hold on those bundles until it's passing over the Mars rover, so that the communication is established, the contact is established, and the data is delivered. So that's very different from how internet works, both on TCP/IP and UDP. And I'm going to run quickly this video so that you see, pay attention to what happens to the units of data as you go from TCP/IP and UDP/IP, which are the two stacks being used here on the internet, and in comparison with the DTN. So if you see at the top, there is a connection established, right, between the two routers. When that connection is not established, then basically the packet is lost. But not only that, there is a handshake necessary to establish the packets. UDP/IP is much simpler because it is not connection oriented. So UDP/IP, you see that as soon as the link is available, the packets go through. If the link breaks, the packets are discarded. Whereas in the last one on DTN, what you see is nodes have a storage. So what happened is that if the communication link is not available, the system simply stores the system simply store the file, sorry, not the file, the bundle, until the contact happens again. And what this illustrates is that in scenarios of high disruption, DTN performs better than the others. This is an example now related to, and this is not an example, but this is a performance comparison that was performed quite a few years ago that compares good put, let's say throughput, as a factor of delay. So on the x-axis, you have the round trip time in milliseconds, and in the y-axis, you have the good put in megabit per second. And what you see on the left-hand side is round trip times that go from 0 to 1 second, which is 1,000 milliseconds. And you see the blue line, which is TCP/IP, starts going down pretty much linearly as a product of or factor of the round trip time. When you go to the run height side on the picture, on the second picture, you see longer round trip times. Now you're talking about seconds, from 0 to 16 seconds. And you see that TCP performs pretty bad in long round trip seconds. Whereas the bundle protocol states, and for this specific situation, states around 10 megabit per second, irrespective of the round trip time. Why is this important? Well, think of the moon. It is estimated that the round trip time on the moon, it's going to be around 4 seconds. Technically it's 1.3 seconds each way, but if you add a relay and more processing, it's going to be around 4 seconds. So what you see here is that at 4 seconds, TCP/IP doesn't work, and even bundled protocol over TCP/IP doesn't perform well. Now you start looking at things such as using the bundled protocol with LTP for those type of links. So that gives you an idea of why DTN is required. You basically is required to have a functioning network that can move data around. Now let's go quickly through some of the progress of DTN, how this evolved. As we said, the first idea came in 1998, thanks to Vint Cerf and some of the folks at JPL. There were a lot of development since then. Just wanted to highlight a few things. In 2008, between 2008 and 2011, there was the first DTN experiment in the deep space that happens on board the NASA Epoxy spacecraft, and DTN was tested, or the bundle protocol was tested over a 81-second delay successfully. Then between 2012 and 2016, the European Space Agency joined the effort, and they performed a successful control of a robotic arm using DTN in the International Space Station. Between 2016 and 2019, NASA successfully tested and set up the first operational DTN network in the International Space Station. That network is still up and running. And earlier this year, and that mission is still ongoing, the PACE mission is an environmental observation mission, became the first NASA Class B mission that uses DTN operationally in a satellite. And that's still going, and NASA is learning big time on it. From our company, Spatium Corporation, we basically are building a DTN platform. That's basically a combination of DTN nodes and DTN management and security. And we're going to be testing the performing a technology demonstration of the DTN platform in the International Space Station later this year. As you may imagine, we're super excited to show the capabilities of the network, being the first commercial DTN network for space. Now, what's next? Well, what's next is really in front of us. It's LunaNet. It's basically the network architecture for lunar communications, positioning, navigation, and timing, PNT. It is an open network, and its standardization and technical specification has been driven by NASA, the European Space Agency, and JAXA as space, the Japanese Aerospace Agency as space agencies leading the effort, and many companies in the private sector as well. One of the key things of LunaNet is that it is first open, pretty much, following the precept of the internet. It is using the bundled protocol as the internet working layer. Supports data communications, user communications, and PNT as well. It goes through the full stack from physical layer to data to networking and the use of the bundled protocol. And also very important, it is the first time such a network devised the concept of a service provider. So LunaNet depicts the concept of the LunaNet service providers, LNSP. So what we see is the same way we have AT&Ts, Verizon's here in on Earth. We're going to have service providers on the lunar surface as well, making the interplanetary internet more than real. And that's going, just to give you an idea, LunaNet is going to be deployed between 2025, starting next year, to 2028, the first phase of LunaNet, and that includes efforts from NASA, ESA, JAXA, and many companies, including Spatin. That's just a view of one key concept of the fact that LunaNet specifies that there is going to be an user lunar segment, both on Earth and the lunar surface, and then multiple LunaNet service providers, LNSP, collaborating to deliver services to users. So for example, an LNSP may have a surface network that is enabled by a lander and a rover. Another LNSP may have a network of satellites and how they communicate together so that users that have payloads on the lunar surface can use the network to send data across between the two locations. So with that, I'm going to close with something important, which is, we as engineers look at, and professionals of different types, we look at, okay, what does it mean? I'm creating, or we are collaborating, helping to create all this. What does it mean? Well, what it means is that from a humanity perspective, we're moving into a new cycle, a cycle in which space has been done primarily from science purposes, where space and space exploration basically meant the same thing. And now we are moving into the space economy. The space economy is a series of interactions of different actors to generate, goodwill for humanity. The importance of data into the space economy is the following. We believe that similar to the digital economy on Earth, the space economy will be based on data. Even more than on Earth. And the reason is that, as you well know, space is very hostile to humans in terms of habitat. So many of the operations that are going to be performed on planetary surface is going to be done by robots. That requires automation, that requires the exchange of a bunch of data to understand how systems operate, and you need reliable performing networks for that. And also, as we move towards the next decade, where settlements on the moon are going to become common, we need the same thing. We need to provide the same support to humans. So there is a bunch of when we look at the space economy, many companies, organizations, governments are working on delivering different assets, different components that are going to contribute to the space economy. And I won't even start on this, but habitats, construction, transportation, energy, etc. All of that requires communications and requires a network. So that's the important. We are the fabric to enable the space economy. And with that, I think the most important thing, this picture is from a movie, but it represents very well the most important part of why communications are important. We have a need, and this is a human need, to communicate and collaborate. The distances make it harder. We need to make sure that we enable humanity to stay connected across the solar system. With that, if you want to know more, these are my recommendations. Start with IPNC. Go to the IPNC website. IPNC is the Interplanetary Networking chapter of Interplanetary Networking Special Interest Group. It's a chapter of the Internet Society. Many good people from technical, policy, many areas that are related to cover and enabling the solar system internet. You get access to general and technical documentation. There are the IPNC Academy webinars that touches on different aspects, from technical aspects to policy aspects. You get access to join the pilot project working group, where you can experiment for real with these technologies. It is open to students, and it is free to join. There is no charge for anything for that matter. So with that, I get to the end of the presentation. I wanted to say thank you, and giving you the invitation to continue exploring space communications and the interplanetary internet. So I think we are something like 10 minutes to go. So I would like to open it for comments, questions, suggestions, etc.